Good evening, everyone. So many reasons to celebrate today. Oh, first of all, I guess I should introduce myself. I'm Stefan Gopel, the director of the Queen's Observatory. Most importantly, I help coordinate some of the people or contribute to the work that some of the key people are doing there at the front here. I'll introduce them in a second. I'm just a manager. However, in 2009, we did this. We organized the International Year of Astronomy. That's a decade ago. In this room, we have many wonderful speakers who came and participated in the IOA 209. Who were present? Not too many, right? Raise your hand if you were here, if you participated in 2009. You did, that is awesome. I had a feeling. Do you guys know, maybe you weren't here, but do you know why we had celebrated the International Year of Astronomy in 2009? Any idea? What was so special about 2009? We were celebrating then 400 years of discoveries by Galileo Galilei, right? Including the sunspots, craters on the moon, phases of Venus. What else did Galileo do that was so important to us, or to our conception of our place in the universe? Galileo postulated that maybe we weren't at the center of the universe. Mathematically, that was not necessary, but it was the first person to actually say that, and that was extremely important. That's what we celebrated 10 years ago, and 10 years ago, we, and that included some people in the room here, made these t-shirts, and I have some collector's items here at the front. I have 6 t-shirts left, and I'd like to give them away tonight because it's a special night. It's also a special night because it's so beautiful outside, and to have you all on such a beautiful night is a treat, but actually I think the treat is going to be yours as well when you're treated by these people here to wonderful views, vistas of the universe with our telescopes the night after we hear the wonderful presentation that you all came here to attend. So, a little bit uncanny for me to use notes, but I have to read them because tonight, as you'll see, is a very special night. First of all, again, as director of the Queen's Observatory, I'd like to extend a very special thank you to the RASC, the Royal Astronomical Society of Canada, that's been with us for the last 10 years or so and has made these events possible, special. Many members, again, who were present in 2009, including Susan and others upstairs, are still with us. That's quite impressive. They are participating tonight. As I said, you'll meet with them a little later on. Susan, perhaps as a faithful representative of the RASC for the last decade, may I ask you to come to the front? I want to thank you specifically for selfless years, inspiring service to the observatory for all these 10 years. And in fact, I mean, month after month for the last 10 years, we've been able to rely on your unshakable enthusiasm and smile. Seriously, Susan has been here month after month, not missing one beat for the last 10 years. And for that, I would like to thank you very much. We don't have an award for exceptional service, but if we did, it would go to you, absolutely. No, seriously, Susan is just exceptional. Well, while you're at the front here, let's take advantage of this opportunity to draw the device that you have for people in the room.
So this is a new thing for the, I think everybody can hear me.
You deserve it.
So this is a new thing for the center. What we wanted to do was we wanted to get out a beginner's observing package to someone, and we also wanted to raise a little bit of money for our outreach activities. Outreach activities include the purchase of the Sky News magazines that you pick up here. Also, we send extra copies of Sky News to the local library systems. They have a subscription, they get 1 copy, they have 15 branches, so we give them a few more to circulate. Also, the Starfinders, the moon cards, and stuff like that you see. Trek. So that's where the outreach money goes. It's a very small fundraising effort. We only sold 500 tickets so that everybody would feel they had a good chance. So tonight we're going to do the draw. And it's the tripod, 20 by 80 binoculars, 3 books, and a planisphere. And Stefan is going to draw the winning ticket.
I love this. Let's open the box.
Okay, close your eyes.
Need money?
You're in it?
Don't even look.
I'm not even
Don't
looking.
even look.
Okay.
Move it
There's
around.
three, there's a lot. Do you know how many we sold?
We sold 451, I believe.
All right. The winner is. I think you should say that.
Susan Biden.
Oh, Brian McCullough from Ottawa.
Oh, that's going on. Great. What's going on? I have to be here, unfortunately.
No.
No? Oh. Yeah. All right. Then Brian's our winner, right?
Brian McCullough is our winner.
Okay. This was that one, right? Well, I should. I'll keep it quick. But you know what? After this, there's a cash for it if you want this collector. I think people can hear me as well. If you want this incredible collector's item, the little cash, I'm happy to give it to you, but I'm left with 6 extra large t-shirts. So if they fit and you have a good reason to have it, I'll give it to you. Our partnership involves not only the RSC, but also the McDonald Institute, so I'd like to invite Ben Tam as our representative of the McDonald Institute to say a few words.
Thank you so much. And today for the McDonald Institute, we have 2 exciting events we'd like to try to advertise it. First one you see before me, that's McDonald Institute Corps. So this is a wonderful opportunity if you have someone that's around the age of 13 towards 18. This is around high school age. This is a free summer camp. There's 12 exciting weekends weeks that we will move on to this sort of camp that is through the summer that we're working with scientists on various different aspects of learning science, learning different aspects of various fields of science that we do here at the university. And the other exciting events we have is what we call the Girls Camp. So this is very similar. This is a 1 week, 5-day long camp. Kids, girls going grades 7, 8, and 9. So again, if you or someone know is a girl that should be doing sciences, going grades 7, 8, or 9, this is an exciting opportunity for them, also for you as well. We do one more exciting note, so I think I'll pass it off. So I don't know how you want to get this on.
I'll leave it there. Sure. I'll save yours. Thank you very much. Such a wonderful partnership that we have now with the McDonald Institute. Well, speaking of which, I'd like to invite Nikhil Aurora and Connor Stone to the podium. I told you we had many reasons to celebrate. This open house has been one of the most popular public event on campus, and we can see by your presence that the events again are appreciated. And I can announce officially that now it's not only are we going to have 1, but 2 official Queens Observatory coordinator, Nikhil Aurora and Connor Stone. So it's the first time in the history of the observatory that we're able to have 2, and that means basically better service for you, more activities. We're very happy to have those 2. So Nick and Connor, thank you so much for all the work you're doing. Yeah, you're good. Oh, you want to make the announcement? That's a good transition for that. Connor, you can stick around as well.
All right. So this particular event is the second of its kind, and it combines 2 of my favorite things: beer and astronomy. So it's called Astronomy Unpacked. It's a world-famous event. It happens in multiple cities across the world, and we're having its 2nd edition on June 13th at the Mansion. We have themes for this event. Today we're going to learn about the origins of everything, but there's also the dark side to it
Connor has been with us for the last 3 years at Queen's, working on his PhD actually with me, I should say, as well as Nico for that matter, both working on properties of galaxies in the universe, typically our nearby universe. I don't know how much you'll talk about that. Not at all. You can ask some questions later tonight. This is a special opportunity also for Connor. Lots to celebrate. Connor next month, actually at the end of June, is going to Germany to celebrate with 39 Nobel Prizes and a number of students from 89 countries around the world. So it's a very special treat that you were invited to participate in that event, and we're very happy for you. In addition to that, just last week, Connor had his very first scientific publication accepted in the prestigious Astrophysical Journal, and that's another great reason to celebrate. Things are going very, very well for Connor, so we're really proud and happy to have him tonight. So without further ado, I'll leave the podium to you and just say that if you want one of these shirts after the presentation, I'll stay by the table and give you what I can. All right, Connor, it's all yours.
Thank you, Mr. Khan. So, where does it all come from? What are we made of? And how did we get here? These are questions that humans have been asking since the dawn of civilization. And today, it's my goal to try and answer those questions for you. So when we look around the room, we see all sorts of different materials around us. Wood in the tables, water and organics that make up us humans, silicon and other metals inside of our computers. All sorts of different materials around us with different properties. But how did they get to be here on this earth the way that they are right now? To understand that, we're going to have to actually learn a little bit about the fundamental nature of all of these different materials. And if you want to study a material at its most fundamental level, you have to pick something to start with, say a cookie. And you start breaking it up. You keep breaking it down until you get to the fundamental cookie, which is a crumb. If you break the crumb up anymore, it's not really a cookie anymore. It's flour, sugar, and water. You keep breaking that even more, and you get down to these fundamental pieces of everything around us, atoms, or elements, as we call them. Now, an atom is made up of a cloud of electrons that surrounds a nucleus at the center. That nucleus is made up of protons and neutrons. And the number of protons determines what type of atom it is, what properties it has. The number of neutrons is critical for its stability, so it doesn't break up into other types of atoms. So say if you have one proton, that's hydrogen. 2 is helium, 3 is lithium, and it keeps going on. You can just make a whole list of these. In fact, scientists have. We call it the periodic table of the elements. So these are the fundamental building blocks of everything you've ever seen, heard, smelled, touched, everything. And it's kind of curious, how did these get to be here in the form that they are? I'm going to actually talk about 5 different processes that created these elements for us to use in our everyday life. They're very cataclysmic events, and we'll break them down one by one. But to begin, we should probably start with the origin, the Big Bang, where all matter and energy was created. So, here we have a picture of our universe when it was just a baby, 300,000 years old. They're very cute at that age. And at this point, all of the elements that the Big Bang was going to make were created. But it turns out that the Big Bang didn't create the elements in the form that we see them today. It would have mostly produced those 3 simplest ones, hydrogen, helium, and lithium. We need the other 4 processes to get us the rest of the way and fill out this table that we take advantage of every day. All right. So let's go on to the second process, exploding massive stars. See, all this hydrogen in the universe would have clumped together into a bunch of stars. Some like our sun, and some much, much bigger. So much bigger that they're really comparable to our solar system in terms of their size. Here we can see the orbit of Earth in comparison to the size of one of these stars. They are really massive. They burn through their fuel very quick, burning through their hydrogen, and eventually they explode in a massive explosion that will actually release more light than our sun will in its entire lifetime. As it does so, it will create a whole host of new elements and spread them out into the universe as a big cloud of gas. And I said they're bright. They can be comparable in brightness to a whole galaxy, which will have 100 billion stars inside of it. These are great for spotting out there in the universe with our telescopes, because they're so bright. All right. Now, all the elements that they produce and spread out into the universe, they actually don't produce all of the elements that we know of. They actually create these ones. A lot of elements that we're actually familiar with in our everyday life. There's carbon, that's what a lot of living things are made of. Nitrogen and oxygen, which we find in our atmosphere. Even table salt is made in these sorts of explosions. So we're starting to sort of fill up on the materials that we are used to. Another one that it produces, which is very important, is iron, right here in the middle. Iron is, of course, useful for everyday life, but it'll also be useful later on in one of the next processes. But you might be asking yourself at this point, how is it that a star, which would have been a big cloud of hydrogen and helium that came together, how does that create new elements? Well, to understand that, we're going to need to learn a little bit of nuclear physics. But don't worry, we'll do it nice and slowly. All right. So, the nucleus of an atom has protons and neutrons in it. And these protons and neutrons are arranged in what would be called energy shells, which we can think of as energy shelves. The higher the shelf, the higher the energy, and the harder it is to get there. So, if a nucleus finds itself with a lot of neutrons, it's actually possible for one of them to hop over to a lower shell and become a proton. In this case, since we've changed the number of protons, we've actually changed what element we've got in our nucleus. This is alchemy. This is how you create new elements. But this isn't the only process. We can describe a full model with a semi-empirical model, which looks something like this. It's scary. I don't even like looking at this. But we can break it down. So, what is this equation telling us? It's telling us how strong these nuclei hold together. The stronger ones that hold together, the better. That means we want to hold together as strongly as possible, then it will be stable. And it organizes this into 4 different processes that describe whether or not it will hold together strongly. First, we think of the nucleus like a drop of water, which has surface tension, and the larger it gets, the more stable it is. Second, the nucleus has a lot of protons in it. And protons have like charges, which means that they repel each other. In general, this means that we should find fewer protons than we do neutrons, because they don't like being stuck inside that nucleus. And third, there's those shells that want to create balance between the number of protons and neutrons. So these two are going to compete with each other in order to determine whether or not one is stable. Finally, the protons and neutrons can pair up with each other in order to pack more tightly onto the shells. So it's actually favored to have an even number of protons and neutrons, if possible. All right. Now, all this talk of protons and neutrons and switching between them suggests a different way that we can write the periodic table. We can write it as what's called the chart of nuclides. Here we have the number of neutrons on one direction and the number of protons in the other direction. So every spot in here is a different combination of protons and neutrons. The black line shows you all the stable combinations. These ones will stick around for a long time. But if you've got too many neutrons, if you move too far this way, You're in the pink region, and some of those neutrons need to turn into protons in order to get you back onto the black line. In the blue region, it's the other way around. The protons need to turn into neutrons. All right, so this can describe more fully all the different elements that we can create. Now that you're all experts in nuclear physics, we can go on to our next process. Stars like our sun also create new elements for our universe. How they do it is quite interesting. First, our sun right now is glowing because of a fusion reactor in its core. It's fusing tons of material every second and releasing a lot of energy. That energy is what creates sunny days for us, like today. Now, it's fusing hydrogen, one of those primordial elements, into helium, another one of the elements that came to us from the Big Bang. So at this point, that's not really helping us further our way into the periodic table. We're just making more helium. But towards the end of the sun's life, it will start fusing that helium to create heavier elements. And when it does that, it actually gets a lot hotter. It'll get hotter and expand a lot bigger. In fact, we can see the sun compared to how big it would get during this stage, and it would get big enough to swallow the Earth whole in its current orbit. Now, while it's doing this, using the helium, it also releases free neutrons that fly through the sun. Those neutrons can land on other atoms that are spread around in the sun. In fact, because our sun is a third-generation star, it will have a sprinkling of elements all the way through it, a lot of those from past exploding supermassive stars that would have been some of the first wave. Now, this means that an iron atom in the sun could have a neutron land on it, and then we can start having nuclear physics happening. So let's take a look at that. We start with our chart of nuclides, and we zoom in on iron. Now this iron atom is just minding its own business in the sun, when all of a sudden, a neutron lands on it, and it moves in our chart. These neutrons are sort of slowly being produced in the center of the sun, and it can take decades to hundreds of years between captures of these neutrons. But slowly, it'll make its way over. We actually call this the slow process, because it's slow. And eventually, the iron atom will make its way into the pink region. And that's where our nuclear physics happens, because one of the neutrons will turn into a proton, and suddenly it becomes a new element. Instead of iron, it's cobalt. This continues to happen for thousands or millions of years. Add another neutron, pop up, now it's nickel. We're creating new elements inside the sun. This process carries on all the way up, wherever it can make it to, depending on how long the star spends in this final stage. As we produce new elements, they're still kind of stuck in the sun, so we can't get them to use in our everyday life. But the sun will keep getting hotter and keep expanding. At some point, it expands so much that it essentially becomes a big cloud of gas. These nebulae, called planetary nebulae, or really just big clouds of gas, they spread these new elements out into the universe for us. If you're a little worried about the fate of our solar system, well, keep in mind that the only reason we're around here today is because past stars went through this process and created the elements that we need in order to survive. So our solar system will one day join these ranks. And in fact, today, we will get to see this one up in the sky. It's called the Ring Nebula. It's quite beautiful. It doesn't look quite like that through our telescope. That's with Hubble. But still, you'll get to see it. It's very special. Now, these nebulae also leave behind a bright spot in the center. That is the core of the star. The center that was originally doing fusion is now left behind as the clouds of gas move out into the universe. This core is the starting point for our next process. Type 1a supernovae start with one of these cores from a star like our sun. If it finds itself around another star, it can start to pick up material from that star. And eventually it picks up so much material, it gets heavy, and starts to redo fusion again. But this time, it's not fusing hydrogen or helium. It starts fusing heavier elements. And this is very catastrophic for that core, because it undergoes another supernova, kind of like that exploding massive star. And now that we know a little bit of nuclear physics, we can understand what's happening to create the new elements in an event like this. So during the fusion, unlike the helium fusion, this one produces a lot of neutrons. In a few seconds, it'll produce an incredible wave of neutrons that can move an element way off base in the chart of nuclides. So this chart shows all the ones that we've been able to create in the lab. And in a few seconds, this explosion will push way out into uncharted territories. It'll add neutrons so fast that it can't decay back onto the black line. It just doesn't have time to get back there. We call it the rapid process because it's very fast. And so we'll create a whole host of new elements in this charged nucleus. The supernova, or the type 1a supernova, will then glow for weeks or months as these elements radioactively decay back onto the stable line. They have to get there eventually. So this glow is actually really useful for us because it identifies what type of supernova and what types of elements are produced in the supernova. All right, on to our last process, colliding neutron stars. See, stars like our sun leave behind a core. Sometimes those supermassive stars also leave behind a core, and their cores are much more intense than ours. These neutron stars are essentially almost like giant atoms, a big ball of pure neutrons, all held together by incredible gravity. This neutron matter is so dense, a thimbleful of it would weigh as much as Mount Everest. These are very incredible objects. Now, when they collide, they splash this neutron material out into the universe. And they do the R process, like type 1a supernova, and also like those exploding massive stars, but they do it way more strongly. They produce some of the heaviest elements that we can find because they're very good at the R process. Now, we've gone through 5 different processes that create new elements in our universe. Let's bring it all together, synthesize this information, and see for any individual element, where did it come from? Here we can once again look at the periodic table and see what the origin was for any of the individual elements. We can see that carbon, which makes up living things, mostly comes from stars like our sun that have reached the end of their lives, and a little bit from those exploding massive stars. The oxygen that we breathe, that comes from exploding massive stars. If you have a gold ring, that would have come from one of these cataclysmic collisions of 2 neutron stars. Iron, that mostly comes from the type 1a supernova, the cores of stars like our sun, collecting material from other stars and heating them up. So this periodic table tells us, for all of the materials around us, where did they really come from? How did it get here? So now I'd like you to look around the room again. Think about the carbon in your body, or the metals in your computer, and the incredible origins for where all of these materials came from. And of course, the delicious science behind it. Thank you.
Thank you, Connor. We're going to take a few questions around about that. So if there are questions, awesome. Okay.
Okay, firstly, I'd really like to thank Connor because he was so helpful when I didn't know where the open house was. And he was just really great. But my question is a very basic one. Actually, I've got 2 basic questions. One is, are we really made, could we say that we're really made of stardust?
Exactly, yes. So, we are stardust, apple pie is stardust, everything around us is stardust, with perhaps the exception of hydrogen, helium, and a few atoms of lithium. So these, hydrogen, like water is made up of oxygen and hydrogen, so that would have come from our Big Bang. Just about everything else comes from some combination of stardust in various forms. Everything around would be created in stars and released into the universe. Yes. And in fact, some of them have a longer story than others. Lead would have come from the Big Bang, been in one of those massive stars and exploded, then found its way into a star like our sun, and got built up until it became the lead that it is now. So some of them have quite a heroic story with lots of explosions along the way.
Question number 2.
Question number 2 is, I always thought that gold was formed by intense pressure on coal or carbon. So what's the missing oh, that's diamonds. Sorry, I was thinking of gold diamonds.
Yeah, that's
different.
diamonds are created by intense pressures like that. But the pressures don't actually create a new atom, a new fundamental piece of the universe. They just arrange it just the right way to make it very pretty. The carbon itself would have been born inside a star like our sun, and then arranged because of that intense pressure under these mountains. Yes?
Any other questions? Ooh. Hey, we're going to go with Alex and make her wish back.
I'm very curious to know how frequent these neutron stars collide. It seems like it would be a very rare instance, and yet maybe that's why it's a digital graphic and not an image itself.
That's a good thing to spot there. Yes, this is definitely an artist's impression. And neutron stars are actually a very new thing in our understanding about the universe. So neutron star collisions were first detected just, I think, a couple of years ago with the LIGO detector. It's that really big one that detects gravitational waves, very slight contractions and expansions of space itself created by these things as they whirl around each other in the last moments before colliding. So we've only actually seen 2 of these as far as I'm aware, and we can't really say at this stage what the rate would be, but it would be quite rare. You have to get the right conditions. 2 massive stars have to leave behind a remnant that finds their way together. So in one galaxy, it's probably a very rare millions of years in between.
Why are boron and beryllium so different as far as their production and having such a small atomic number?
So, the 5 processes that we talked about are not the only ones that produce new elements. In fact, we can even create elements like gold inside of a nuclear reactor. So we can actually make new elements. The gold is radioactive, so you don't want to make a ring out of it. But we can make our own elements, and cosmic rays can make new elements as well. So these are high energy particles that are flying through our universe all the time. Our Earth is a very special cushion that protects us from a lot of these rays. But out in space, you're just subjected to whatever is there. And sometimes those will collide with another particle and break off a chunk of it. And that's actually where we get most of the boron and beryllium. It turns out that there's actually a bit of a stop between naturally building up from hydrogen, helium, lithium, beryllium, and boron. That doesn't naturally happen. So when a star like our sun is using helium, it doesn't fuse it into lithium and beryllium. It jumps straight to carbon in what's called a triple alpha process. It basically, you have to get 3 of them together in just enough time in order to jump your way from helium
this one. What is the yellow squares kind of reaching towards the top of the name?
Good question. So the colors on here show us the different ways that that combination can decay. So if you're over here, that means you would convert neutrons into protons. In the yellow region, that means you undergo what's called alpha decay. Essentially, a helium atom just flies away from your nucleus because it's like I'm much more stable on my own than you are in your giant blobby nucleus. So it'll just shoot out of the nucleus and it'll move you down in both protons and neutrons, and it'll try and get you back onto the black hole. The green is fission, like we use in our nuclear reactors to break apart larger nuclei. These ones are so big that that big equation doesn't even apply as well anymore, and they start to wobble until they break up into two smaller nuclei. It's fission just like in a nuclear reactor. So those are what the different colors mean. Each one is a different type of reaction, or black, or no reaction. Yeah. Thank you.
All right, so William over here has a question, but he's a bit too shy, so I'm going to say it for him. If stuff is made from matter, what is made from antimatter? Great question.
Ooh, good question. Antimatter, actually, as long as it's only around other antimatter, it behaves almost identically to regular matter. You could create this whole charge with antimatter. It would look the same, it would behave nearly identically. The difference comes from when they interact with each other. If antimatter ever finds regular matter, they completely blow up. Yes, exactly. So when they find each other, they annihilate and leave behind a lot of energy. So in terms of what antimatter would do in these processes, it would be the same. You could have a whole star made of antimatter that creates new antimatter elements. The problem is, there's just not that much antimatter around. We won. We were the dominant form of matter. All right, thank you for your question.
I've stolen the microphone from Nick. Thank you so much, Nick. And on that note, I'd like to thank our speaker and Nick, but especially our speaker for a fantastic presentation. And just before I turn the microphone over to them, I have two questions. First, if you followed, quick question, just to see if you followed. Everyone followed this awesome presentation. William, perhaps, this is a trick question. I'm going to ask you, but for everyone else, and I just don't want to point at William in the room, I'm going to ask you, how old are you? How old are you? Think about it, okay? Think about it hard. What is the answer? How old are you? You may say 8 years old, 7 years old, 10 years old. We may say 40, 50. Wrong. All of us wrong. How old are we if we listened to the presentation? We now know that we are?
Around 13 million.
Oh, you're good. Oh my God, you're good. I think I have a t-shirt for you. It's going to be big a little bit. You said 13 billion. That's ballpark good. Or the order is right. We're about 5.7 billion years old. All that matter into us, again, is formed from typically 2 to 3 stars. Remember that number. And now you appreciate, thanks to the great presentation we had, that we are indeed stardust. And we're all about the same age. 5.3 billion years old. I'm really torn about these t-shirts because I'd like to give them all to you. I have 5 or 6 here, and I thought to make it easy and simple, I would offer 1 t-shirt per person who asked a question today. Is that fair? Because otherwise, it'll be tricky to. So if you asked a question tonight, I have a t-shirt for you. Otherwise, I will truly turn the floor over to the organizers, and that'll be Nick or Laura. So come and get your t-shirt when they're done.
Right, so once the 5 people who are going to collect the t-shirts will come to Stefan. We have a great turnout today, and so that means that you all get to experience what physics at Queens is all about, and that starts with the color of the ticket that you have. So I would ask you all to look at the color of the ticket that you have right now. I'm going to use the laser pointer. Okay, so we have 4 stations. We're going to start with the black colored ticket. If you have a black colored ticket, you're going to follow Ben out to Sterling Hall, who's going to take you to the McDonald Institute Visitor Center. We're going to make our way backwards now. If you have a green ticket,